Troubleshooting. With transistor equipment, you go about troubleshooting in much the same way as you do with vacuum tube equipment. There are a few very important differences, which we shall cover in this picture, but by and large, the approach is the same. For instance, the first step is a careful visual observation. We look for obvious causes of trouble: a frayed cord, a defective plug, rust or oil or dirt, hardware that's missing or not working properly. 10 or 15 minutes spent on this kind of inspection is always valuable. It may not only solve the immediate problem, but also prevent trouble in the future. Whether the equipment uses transistors, tubes, or both, the visual check should definitely include fuses and fuse holders, the cabling and cabling connections, loose, missing, or scraping front panel controls. Inspect interior for broken wire and wire connections. Once the trouble has been localized to a particular module, it should be carefully inspected. The inspection of a module should include the following items. Look particularly at the printed circuit boards. The board itself may be cracked. This is a frequent source of trouble. Or a portion of the printed conductor may lift away from the board, become delaminated. Now, if the transistor set is battery powered, the battery terminal should be inspected for corrosion or a possible loose contact. And make sure the battery is properly installed. Assume nothing. Usually transistors are soldered directly into the circuit. So if the equipment you're troubleshooting ever worked at all, it isn't likely that any transistors are missing, interchanged, or improperly mounted. But there are cases where plug-in transistors are used, like this. And you have to be just as suspicious of them as you are of plug-in vacuum tubes. In troubleshooting circuits where plug-in transistors are used, check the following points. Does the circuit call for a PNP or NPN transistor? Is the type number correct? That is, does the type number on the transistor match the type number indicated on the circuit diagram? Is the transistor mounting correct? That is, are the emitter, base, and collector leads of the transistor placed into the right holes in the socket? Well, the leads of many transistors are spaced like this. They are the emitter here, the base here, and the collector here. There is, of course, only one right way to match leads and socket holes, as indicated by spacing, guide marks, or labeling. If the leads are too long and flexible, however, it's easy to bend them enough to plug them in the wrong way. Sometimes you'll find leads so badly bent that they touch each other, or they won't be plugged in far enough to make contact with the lugs of the socket. If the wrong transistor has been plugged in, or the right one the wrong way, it may have been damaged. So may other transistors, depending on the circuitry. They'll all have to be tested. Now, the troubleshooting procedure that was originally worked out for vacuum tube equipment follows a distinct logic. First, the visual inspection. Power off. If that doesn't turn up the fault, we check the main circuits for shorts. Power off. Then we check the operation, power on, for a quick clue that will sectionalize the trouble. If this doesn't do it, we test the power supply, which is a kind of sectionalizing. If the power supply is okay, we sectionalize to a group of stages, and then localize down to one stage. Then we usually test the vacuum tubes in the suspected stage. And finally, we isolate the trouble to a defective part or parts. With vacuum tube equipment, once the faulty stage is known, we unplug the tube and test it. But we don't usually do that with transistors. In the first place, as we said a moment ago, transistors are usually soldered into the circuit. Now, unsoldering them can be a tricky business and should not be done unless absolutely necessary. Secondly, the transistor is probably not defective. This is one of the big differences. If a vacuum tube stage acts up, the cause is likely to be in the tube's burned out heater. But transistors do not have heaters, and in that respect are more rugged. When a transistor stage goes bad, the trouble will be in the external circuit more often than in the transistor itself. Not always, but often enough to justify forgetting the sixth step in most instances. We don't substitute the transistor test for the tube test, unless we're dealing with plug-in transistors. Now we'll apply this whole procedure to a transistor set. The visual inspection didn't give us the answer. So we'll go on to the next step, and with the power still off, we'll check for shorts. Please note, I said power off. We don't apply power to the set until we're absolutely sure that operating it won't cause more damage. Also, as you know, disconnecting the equipment under test is standard precaution whenever an ohm meter is used. We'll look for main circuit shorts by measuring resistances at the key points shown in the manual. Let's begin by measuring the resistance between the supply distribution point and ground. Whenever you do this kind of... No, hold on a minute, please. I want to explain this first. It underlines a basic fact about transistor circuits. If we were testing a vacuum tube circuit with the heater power switched off, the tube would not be conducting. But a transistor does not have a heater. When a voltage from any source is introduced into this circuit, the transistor normally conducts. Now the voltage will affect not only the transistor, but also the polarized electrolytic capacitors. They may be damaged if any voltage that's introduced isn't low enough, or if the polarity is wrong. When we check for a possible short by measuring the resistance between the supply distribution point and ground, the ohm meter puts out a test voltage. We have to be absolutely sure about the polarity of this output, and also take care that the output voltage doesn't exceed the value normally present in the circuit. The ohm meter's output voltage and current are determined by the range switch setting. Observing polarity is simple enough in theory, but in practice, the unmarked probes may lead to a mix-up. On the electronic multimeter we're using, the TS505, the ohms probe is the positive probe. But on the familiar TS352 multimeter, it's the common probe that's positive. In the example here, whichever probe is positive is applied to the supply distribution point. The negative probe goes to ground. Under operating conditions, the supply distribution point in this diagram would always be positive with respect to ground. In this case, resistance readings at checkpoints are satisfactory. However, if the resistance of a main circuit shows up reading substantially below normal, don't turn the set on. There's a short somewhere and it must be found and corrected first. This will require further measurements with the ohm meter, and each time we have to be painstakingly careful about the polarity and value of the ohm meter's output. Say there are no shorts, or we clear up those we find. Now we can apply power and check the operation of the equipment. At this point, it's a good idea to go to the performance checklist in the manual and follow the sequence of operations outlined there. Once again, don't overlook the obvious. When the power was switched on, did the dial lamps light? In equipment with panel meters, do they read normally? sensory indications, sight, or sound, or touch are not quite as helpful with transistors as they are with vacuum tubes. With power on, the glow of the heater in tubes is normally visible, and you can feel them warm up. But a transistor never glows, whether it's working or not, and in most cases its normal temperature is about that of the air around it. Nonetheless, even when a set is completely transistorized, it still pays to look and listen for operational symptoms that may be a shortcut to the trouble. Touching certain components may also add information. In a television receiver, for example, the picture tube itself makes an excellent test device. For radio reception, the loudspeaker serves a similar purpose. Is there a rushing noise? And can it be varied by adjusting the volume control? Or do we hear too much hum? Is the signal weak or distorted?
I'm thinking tonight about you are.
Or do we get nothing at all, a dead receiver? With experience and help from the checklist in the manual, a repairman can quickly interpret these symptoms, very often sectionalizing or even localizing the malfunction without further delay. Before we leave this, let me add a word of warning. One familiar technique for checking the operation of vacuum tube receivers must be avoided with transistors, the grid disturbance check. That is, temporarily short-circuiting the grid of a tube to chassis ground and listening for clicks. This is standard practice when troubleshooting vacuum tube circuits. But its equivalent here, shorting the base lead of a transistor to ground, should not be done. This action creates a surge of current, which, after amplification, may damage transistors in succeeding stages. The next step is skipped. If the equipment's performance has already indicated that power is being delivered, or where a front panel meter is provided for reading B+ voltage during operation. One way or another, we have to be sure before we go on that the trouble isn't due to the power supply. Where more than one power unit is used, each of them should be checked out. And each measurement of output voltage should be taken under load conditions. With a battery-powered set, don't forget that dry cells gradually deteriorate, and that the output of these batteries may now be below the required value when measured under load. When the first 4 steps of the troubleshooting procedure don't give us a conclusive answer, it's time to inject a few test signals in order to sectionalize the problem to a group of stages and then localize it to a single stage. We need a signal generator to inject test signals. Also, some means of indicating output. A speaker will serve in some cases, where the shape of the signal should be checked visually, as in troubleshooting pulse-forming circuits, an oscilloscope is used. But a very common indicator is the voltmeter, a battery-operated meter such as the TS352, or an AC-powered meter such as the TS505. The TS505 has a much higher input impedance and is therefore more suitable for troubleshooting transistor circuits. Assuming that the equipment can be broken down into 4 sections, either of 2 methods for sectionalizing trouble may be recommended in the manual. The first method is signal substitution, which means we leave the output indicator connected at one point, on the right side here. And we insert the test signal at a convenient point, which roughly divides the untested sections of equipment in half. If we obtain the proper output, it will indicate that all sections between the inserted signal and the output are working properly. Then the test signal is inserted at another convenient point, which roughly divides the untested sections of equipment in half. Output is proper. Insert signal at next convenient point. Output is improper. Defective section has been located. If we obtain an improper output on our first test, it would mean one or more sections between the inserted signal and the output are possibly defective. Then, by eliminating those sections working properly, as evidenced by receipt of a proper output, the defective section is pinpointed. Signal substitution is usually called for in checking radio receivers and the AF circuits of transmitters. The other method the manual may specify is signal tracing, which works the opposite way. The point of signal injection is always the same, and it's the output connection that's moved around. This tracing technique is customarily used for the RF circuits of transmitters and for pulse-forming circuits. However, when a signal is injected into transistorized equipment, there is one big danger. Unless we're careful, the signal generator will overdrive the transistors and damage them. Therefore, we set the signal voltage at its lowest level. We turn off the equipment under test before connecting the signal generator leads. Then we turn the equipment on, and if necessary, increase the signal strength gradually. But we don't ever try to force an output by going above the normal voltage level. Finally, we turn the equipment off again before disconnecting the signal generator leads. The result of all this detective work is that we now know where the trouble is. We've localized it down to one stage. Now we have to isolate it, find out what it is, the particular component or circuit condition that's causing the malfunction. It may be a bad transistor, although, as we have said, transistors are less likely to fail than vacuum tubes. Or it may be in the external circuit, a faulty associated component, or printed conductor, or solder joint. We'll find the answers as we do with vacuum tube circuits, by measuring voltages and resistances. But there are complications here. Transistor circuits present a greater variety of circuit conditions. Differences in value of a fraction of a volt may be extremely important. The supply distribution point is not always positive, as it usually is with vacuum tube circuits. In a transistor circuit, the supply distribution point may be negative or positive with respect to ground. Moreover, we have two basic types of transistors to deal with. In an NPN transistor, the collector should be positive with respect to the emitter. But in a PNP transistor, it should be negative with respect to the emitter. In order to show how troubles in a transistorized stage are isolated, we'll connect these two into typical circuits. Let's make the supply voltage in each case plus 10 volts. And the normal readings at the NPN transistor with respect to ground are 0.4 of a volt at the emitter, 0.7 of a volt at the base, and 9 volts at the collector. At the PNP transistor, again with respect to ground, 9.6 at the emitter, 9.3 at the base, and 1 volt at the collector. Remember that these are normal values, so we'll note them below for reference later on. Now, suppose that when we take voltage measurements at the emitter, the base, and the collector, we find that all three are normal. The stage doesn't operate properly, but the voltages check with the book. This is comparable to a condition found in vacuum tube stages, and the causes are the same. An open capacitor or a detuned transformer. If it's detuning or misalignment, look for open or shorted tuning capacitors or maladjusted tuning slugs. Or shorted coils. If the transistor voltages are abnormal, all of them or any one of them, then we can pinpoint the trouble by checking three relationships: base voltage to ground, base voltage to emitter voltage, the forward bias, and collector voltage to emitter voltage. If the readings were normal, the base voltage to ground would be as shown here. The base to emitter voltage, that is, the difference between the two, would be 0.3 of a volt. And the difference between collector and emitter would be 8.6 volts. Notice that as we've set up the example, the differences are identical for both the NPN and the PNP transistors. All right, we'll try some interpretations. Say that the base voltage to ground is practically normal, but the emitter and collector voltages are so far off that when we measure from base to emitter, we get 0, meaning no forward bias at all. The transistor is cut off, causing the collector-emitter voltage to approximate the supply voltage. This indicates an open external DC emitter circuit. Once again, base voltage to ground, normal. Base to emitter, 0. Collector to emitter at approximately supply value. Look for an open in the external emitter circuit. Now we'll make several significant changes. This time, the emitter voltages are such that when we measure from base to emitter, we get a very high reading, 0.8 of a volt, which is almost 3 times the normal difference between base and emitter. Look below at either normal values table, and you'll see that the difference between base and emitter should be 0.3 of a volt. The trouble is in the transistor, an open internal emitter, or an open internal base. In both cases, the base voltage was normal, and the collector to emitter voltage was at supply value, or nearly so. But we had a high forward bias the second time around, and that means either the emitter or the base is open inside the transistor. Both these diagrams show an open external base circuit. Notice that in both, the base to emitter voltage is 0, and the collector to emitter voltage is at supply value. However, the base voltages to ground differ. The NPN base is 0. The PNP base is just the opposite, supply value. That makes another one for our chart, an external open in the base circuit. So far, the collector to emitter voltage has been consistently at or near the value of the supply voltage. But when the external collector circuit is open, the collector to emitter voltage drops to 0. Also notice that in this situation, the forward bias, base to emitter, is normal, even though the base voltage itself is a little low in the NPN transistor and a little high in the PNP. The forward bias is still normal, but once again, the collector to emitter voltage approximates supply value. This is collector trouble 2, an open internal collector. This completes the list of opens. If you study it, you'll see certain patterns. For example, if the base to emitter voltage is normal, the fault is with the collector, internally or externally. If the base to emitter voltage is abnormal, the fault is with the base, or the emitter, or their circuits. Also, if you get a 0 reading for either of these relationships, check their external circuits. If the readings are abnormal without dropping to 0, the trouble is in the transistor itself. Incidentally, if the base to emitter reading shows a reverse bias with the base voltage normal and the collector to emitter voltage much lower than normal, the problem is a leaky transistor. That is, far too much current flows between the emitter and the collector, although the transistor is reverse biased between base and emitter. Two types of shorts in transistor circuits should also be mentioned here. One is a shorted capacitor in the emitter circuit, here in an NPN transistor, and here in a PNP transistor. This is indicated by high forward bias, normal base voltage, and low collector to emitter voltage. The other is a short in the input transformer, which will require a modification of our diagrams. The big clue here is that the base voltage is the same as the collector voltage of the previous stage. This means the base voltage is high in an NPN transistor, very high, and very low in a PNP transistor. The base to emitter voltage is higher than normal, and the collector to emitter reading is much lower. As you see from the chart, both types of shorts give a high forward base to emitter bias and a low collector to emitter voltage. But only a short in the input transformer will have the effect of producing a high voltage at the base of an NPN transistor and a low voltage at the base of a PNP. If we have a transistor that is open internally, as either of these two sets of readings would indicate, it will have to be removed and replaced. But it's wise to double check before getting involved in unsoldering and soldering. There's a simple way to confirm the diagnosis: the transistor in circuit resistance test. Power is turned off, of course. Power transistors would be measured with the ohmmeter range at R times 1. But for small signal transistors, the range must be raised to R times 100. We measure the resistance between base and emitter. Then we reverse the test leads. If the measurement is identical both ways, there is an open between the base and emitter. We actually measured the resistance connected externally between emitter and base, in parallel with an open transistor. If the reading one way is high and the other way low, no open exists between the two. In this case, the external circuit resistance is shunted by the high reverse resistance one way and by the low forward resistance when the leads are reversed. Then we do the same thing with the base and collector. As we said at the beginning, troubleshooting transistor circuits follows the same basic logic as troubleshooting vacuum tube circuits. The differences grow out of the characteristics of transistors and their associated components. For example, you cannot conveniently remove them from their circuits for individual testing. You should not overdrive them or subject them to reverse polarities. And the most important thing to learn is how to correctly interpret voltage measurements.